what I am going to talk about, as I heard that there are more than 50% master students also, so I have prepared my slides little bit basics also to understand the things in a more molecular level, and I also changed my title little bit so that it could be more on crisp, but the topic remains the same. So the title of the topic I have given, tuning the fluorescence blinking in single molecule materials, as this school is basically molecular materials. So although molecular materials definition is so many fascinating way to define it, but let's try to understand those things. So what we do basically in our lab, we work on the fluorescence material, we tuning their fluorescence properties for various applications, and one of the major important properties what we do the blinking analysis and blinking manipulation. So I'll give you some very important examples and their applications, but before that let's try to understand what is blinking at a molecular level. So for that, first of all, let us go and try to understand the what is fluorescence, because as master students might be there a little bit. So before that, let me show you that here is the Himachal. I hope everybody knows it is in the upper hills, and this is our beautiful campus. You can see already in the monsoon time, whatever you had it. So the clouds are basically just kissing us all the times. And there are two campuses. One is this is called, we call as North Campus. Here is the main administrative building is there. This is the guest houses. Professor Pradeep was one time there, so we have a very beautiful guest house as well. And these are the all these hostels and all these things. And this is another part of the campus. And here are some beautiful images, as you can see in the upper hills. So this is basically a beautiful lake which is called Parashar, which is Rishi Parashar was there. And you can see the highest, longest tunnel in the highest hills, which is called as the Atal Tunnel, which is in the Rohtang Pass, which basically connected the upper hills very nicely, and whatever the 5-6 hours drives, now you can drive through within half an hour across the road. So these are the very beautiful pictures. Okay, now coming to the topic, whatever we are talking about. So let us try to understand very fundamental and basically what is all about fluorescence if we go to the very basic energy levels. So if you see any kind of molecules, here is a simple example of, let's say, benzoic acid. We have sigma, pi and non-bonding electrons, and we have this kind of electronic energy levels. So as per the selection rule, we will have the transition sigma to sigma star. So we have the bonding as well as the non-bonding or anti-bonding. So we have the sigma to sigma star transition, which basically happens in the for UV below 200 nanometer, and then we have the pi pi star transition and n pi star transition, which basically happens in the UV towards the visible, and some of them is basically in the NIR region. So this basically happens in every of the molecules of the materials. Now, depending on the electronic configuration or electronic arrangement, one can arrange the electron like here. We can, as per the Pauli's exclusion principle, we can arrange these electrons here, 2 electrons, then 2 electrons, then 2 electrons, and we have several pi states as well as several pi antibonding states. So whenever we have the filled electrons, that's what we call it as HOMO, and then we have the LOMO. So whenever these electronic energy levels of the pi pi stars falling in the UV visible region, that's why electronic spectroscopy happen, especially the fluorescence spectroscopy happens, right? So if we go further down to the energy levels, if you see here that we have the different electronic energy levels, we have arranged the electrons, and this is, we call it as HOMO, highest occupied molecular orbitals. In case of pi electrons, we can call it as pi molecular orbital, and that also we can in terms of the electronic spectroscopy, if we think about the selection rule as well as the spin multiplicity, then we can call it as singlet state. In singlet state, we have these 2 paired electrons. That's why we call it as S0, and this is what basically we call it as S0, singlet ground state. So in a similar way, if we think about the LOMO, the first one, that we can call it as first excited state. How it could happen? If we push one electron here with the same spin to the upper state. So that basically gives you the S1 state, because it is the first excited state with its similar pair, and that's why we call it as S1 state. Whenever this spin is basically flipping, and as we don't need to follow now the Pauli's exclusion principle, it could be paired, and that gives you the spin multiplicity twice s plus 1, which is basically 1, and that gives you 3, and that's why you have the triplet state, and that's what we generate the diagram which is basically we call it as Jablonski diagram, right? And whenever we have these energy differences falling within this electromagnetic spectrum, we have the very high energetic gamma rays to the radio frequency region, but whatever the things or whatever the materials, either the molecules or the molecular materials, whatever you are doing, that basically falls under the UV visible region. So whenever this energy matches with of these things, then we have the electronic excitation. And you can see here that if we think about a simple and principle diagram, we think about this is the S01, this is S1, and then that electron could be excited to the higher unoccupied molecular orbitals. On that case, S1, S2, S3 higher energy state could be generated, and we will have all these vibrational levels. And then as per the selection rules, we can have the excitation whenever IGNOU is coming, and then electronic excitation will happen to the different electronic states as well as the different vibrational states, and that is we call it as vibronic transition, right? And this is basically in terms of the electronic excitation, and we call this as absorption as well. So whenever it happens in the S1 state, this is, you can see that this is a broad spectrum is being happened in the absorption. It could also in the S2 states, we have another spectrum, and all will follow this kind of transition, right? Now, as we excite the molecules, as you saw Professor Patra was also talking about in the morning, that whenever we have the molecule in the excited state, they have different type of relaxation process, and this relaxation process can give you different type of signatures, and one of them is basically the luminescence, right? We have both radiative and non-radiative transition, and that basically defines you the efficiency as well, efficiency in terms of the fluorescence intensity, or we can think about the quantum build, which is basically given by Kr plus summation of Knr. If we want to write here, Knr is all the different type of processes, proton transfer, electron transfer, energy transfer, intersystem crossing, all these things. So one of the emissive process is basically what we call it as fluorescence. So if you see a very simple Jablonski diagram here, so this was in the left hand side, whatever I have shown you. Now whenever it comes to the relaxation process, so we will have all this excitation coming down to the S0 states, vibrationally 0 states of the first S1 state, and then you have the emission process, which basically gives you this kind of emission. So we will have the absorption as well. We have the absorption, which is basically S0 to S1, S0 to S2, and so on. But while we will have the emission, in principally following the Kasa's rule and the Vavilov's rule, emission always happen from the S1 state, and we will have the fluorescence, and it has also the chance to go to the T1 state, that basically via the intersystem crossing, and then you will have the phosphorescence. They have all the different time scales, that what I am not going to discuss those things, but these are basically the principles. And if you think about in terms of the excitation, as you can see here, the similar graph has been shown here, that we have the different vibrational levels, and that whenever we have the excitation happens, so we will have this absorption spectra to different kind of vibrational levels, which gives basically we call it as overtone. So this is a fundamental transition 0 to 0, and then you have 0 to 1, 0 to 2, 0 to 3, and so on. In a similar way, or in a reverse way, if we follow the mirror symmetry rule, on that case what will happen, all this coming to the relaxed S1 by 0 states, and from there you will have the emission, and you can have again all this emission process, which is basically giving the mirror of the absorption. So this is, we call it as mirror symmetry rule, and it basically follows in the molecules which are isolated and not disturbed by the environment. And based on this one, we will have this kind of broad absorption spectrum as well as the emission spectrum, and this shift we call it as Stokes shift, right? Here is the schematic diagram, and one can see that how it is happening from S0 to S1, and then it comes to the T1. Some of the molecules will be coming from S1 to again S0, which is giving you the fluorescence, and this is coming to the T1, that gives you the phosphorescence, right? So this is all basically similar properties in terms of the molecules. As we are talking about, Professor Pradeep also was telling that whenever organic people tells is a molecule has a defined structure, and if you have the defined structure, it has the defined electronic states. But whenever it comes to the molecular materials, its definition is in terms of the clusters right now, but molecular materials could be several ways we can define it. But whenever you have the molecular materials, then these electronic energy levels are basically revised in the sense because of the several possibilities. What are the possibilities? Now, if we come to the molecular materials, like for the nanoclusters as well as the different type of quantum dots or the several other dot materials which are falling under the definition of the quantum confinement as well as the molecular materials definition, what happens basically on that case, these energy levels are basically modified. So, if you see here, now whenever we have these molecules, we have this S0, S1, T1, very simple Jablonski diagram, very simple electronic excited states. Whenever we have these molecular materials, we now call it as bands, and these are basically we called it as band materials. Band materials means we have the valence band as well as the conduction band, and we have the electron hole pair creation by the excitation that basically creates the exciton. And because of this exciton creation, whenever they are having the radiative recombinations, as was talked by Professor Patra, whenever we have the radiative recombination, we have the emission or we have the fluorescence. If we have the non-radiative recombinations, we do not have anything. But interestingly, what happens here, that in case of the molecular material, so in terms of the molecules, we have a very defined S0, S1 and their vibrational levels, we have this excitation, we have this emission. Now, whenever this kind of molecular materials or the band gap materials comes, then the modification happens here. You can see this is molecules versus molecular materials. So, whenever we have the molecules, we have a very defined absorption as well as the emission spectrum with the absorption maxima somewhere here, emission maxima somewhere here, and this is the Stokes shape. Now, when we have this molecular type of materials, when we have the band gap, what the things happens basically, you have different type of excitation happens because of this increase in density of the states, and we cannot avoid those things both in the ground state as well as the excited state, and all this collectively gives you a very broad absorption spectra. You can see here that the band edge, what we call it as band edge, which is basically similar to a transition from S0 to S1, here is the band edge, this part which is the lowest conduction band and highest valence band, this is we call it as band edge. And apart from that, the higher energy states which are having higher in energy, that basically appears here. So, this is my band edge, and then we have different type of absorption. Whenever you are exciting anywhere of this absorption envelope, you will have this emission intensity. So, this is one of the critical point to consider in terms of the molecular materials, which basically creates the complexity as well. In case of molecules, you have very similar type of absorption and emission feature, and you have the absorption maxima, you excite, you will get the emission maxima. In this case, you have the critical states, and not only this one, yes please, not only this one, the other important problem, it is not only problem, at the same time it is also giving you a lot of facilities to work for the materials. So, if you compare here, that whenever we have this kind of different type of excitation happens, we have all this kind of excitation. So, in case of molecular type of materials, if we think about the quantum dots, which could be core cell structures, which could be this kind of metal clusters with a undefined right now. Initially, we had like as we are talking about the very familiar materials is AU25, what people gives the examples. Now, you see that the number is increasing. So, whenever the number is increasing, this band also will be manipulated. And on that case, we are not in a position to say that whether this could be molecular materials also or not, because it again close to going to the bulk situation. So, we do not know this one, this is a debatable topic, but we can think about. But whenever we come to the nanoscale part, absolutely what is happening, that this is my band edge excitation, and then you have the absorption increasing. And in this way, basically quantum yield increases. Why quantum yield increases? Because here the excitation cross section is much more in these cases, and this happens in this kind of quantum dots materials. And as in the morning also is being discussed, and I hope that everybody will be knowing that because of this kind of molecular materials, as with the size changes, and if it follows the quantum confinement within the 10 nanometer size, starting from the, let us say, 0.5 nanometer, what happens basically, it basically tunes its band gap, and then you have the different type of transition happening from the UV to the IR or even more IR range. So, that basically the beauty of the molecular materials, where or the quantum dots or the other kind of materials, where you can tune or modify the system with their synthesis process and can tune this emission process very easily, which is otherwise difficult in case of molecules. Because as you know, some of you might be working on the molecules in the NIR emission. As you know, the quantum yield is basically decreases in the NIR region. There are several factors why it is decreases, right? But so far people are working on the invisible region of the molecules. But in case of the molecular materials or in terms of this kind of quantum dots, you will have the facility that you can tune this band gap with increased quantum yield because of several factors. Now, this is one of the things one has to remember or to understand, that how this could be utilized for different type of applications. Right. Now, one more factor, like in case of in terms of the molecules, we have a predefined structure with its some kind of functional groups. Whenever we think about the molecular materials, as you are listening from the beginning, and some of you already know, that the surface properties. We do basically surface chemistry, as Professor Pradeep showed, that there will be even the core exchange, the atomic exchange happens, we can do the ligand exchange, we can do the surface exchange. And whenever we have different type of surface ligands, because of their electronic configuration of the surface ligands itself, because we have a lot of oxygen group, lot of nitrogen group, a lot of other groups, a lot of peptides as well, that can tune your band gaps, that can modify your band gaps. And not only that one, as Professor Patra told, that because of this one, you can have a lot of trap states. Because whenever some excitation happens, if this excitation happens, we have a very nice electron hole pair and it can form the exciton. But what could happen? Because of the surface ligands, they are having some kind of dark state, we can call it as, where the electron after the excitation can get trapped, which you do not have any kind of emission. At the same time, not only the electron, the hole also could be trapped, and this could be deep trap, this could be swallow trap. Whenever you have the deep trap, swallow trap, depending on the time scale of those trap states, you will have the different type of dynamics. And that basically tunes the optical properties of this kind of materials. Okay, not only this one, as you see that in a simple excitation, we have the exciton formation, as you can see here, but in a similar way, we have the bi-exciton formation. And whenever you have this bi-exciton formation, because of this surface chemistry or some other chemistry, what happens, that either electron could be lost or the hole could be lost. On that case, you can have the trion formation, and this trion could be positively charged as well as the negatively charged. As you can see here, that whenever you have the two holes and one electron, that we call positive trions. If you have one hole, two electrons, we have the negative trions. So, in a simple Jablonski diagram in a molecule, I had S0, S1 and triplet state, right? Here you can see what are the different type of complexity arises. If you have this kind of different type of systems present, so I can have all these states present here. And that basically leads, whenever excitation happen, that could be present in any of these. And that basically creates the problem in case of the molecular materials. So, in one hand, it has the advantage, in other hand, it has the disadvantages. So, if you go in a little bit understanding, so this is the molecules. Now, if you come to the molecular materials, instead of having S0, S1 and T1, now whatever we are calling it as off state or dark state, and that could be either your trionic states or some other states which basically trap the excitation electrons on that state, and during on the time, and this time scale is very large. If you have this large time scale, so what it could happen, it can stay for a longer time. So, on that case, you will have no emission. So, you have S0, S1, S1 basically call it as on state, and that basically gives you the emission on and off here. But here you have another channel apart from the triplet state. Triplet state is also kind of dark state, which is very small time scale, but it is a large time scale. It can keep all the times, and then you have this kind of blinking phenomena, whatever you are observing here. So, this is the thing you can see. This is the real video what we have captured in case of quantum dots in my lab. Whenever you are capturing a single this kind of molecular materials or the quantum dots, and if you shine the light, whatever the respective light you required, if you have the emission, let's say at 700 nanometer, you use the respective excitation source, and it is the same material. You have synthesized in the same system, but you are having a different type of blinking behavior. They are still blinking, some of them are gone dark, right? So these kind of things is very, very interesting in one hand, but it is difficult to get whenever we do in a solution phase or bulk phase. And that is why the single molecule spectroscopy or single molecule microscopy plays a major role. And that's why single molecule spectroscopy is very, very important to understand the blinking phenomena, because if you understand the blinking phenomena, you will have lot of advantages. So I'll show some of them very soon. So you can, yes.
So the inter-system crossing is happening due to the phosphorescence?
No, phosphorescence you do not consider this one. Phosphorescence is different. Phosphorescence is here. Phosphorescence is always happen from the triplet state. Here we are talking about some other states created which is not intrinsic for the material or which is not intrinsic for the molecules. Intrinsic is what? S0, S1 and triplet state. You cannot avoid those things. Either intersystem crossing will happen or not, that is a different phenomena by which phosphorescence will happen. There is a different story that if you have this energy difference between S1 and T1 which is within the 0.3 milli-electron volt, on that case you will have the sufficient energy transfer and it can also come to back to the S1 state, and then again you can have the fluorescence which we call it as delayed fluorescence, right? But that is a simple intrinsic property. But this is something new which is being created. It could be created by the buffer itself, whatever the buffer or the medium you are using, or it could be created by the surface ligand itself, by which you have the different type of trap states. So this is nothing to do with the phosphorescence, it is the new states created. Phosphorescence is sitting here, right there, you can see here, this is my phosphorescence, and the time scale is completely different. Phosphorescence happens from microsecond to second, and this happens in the millisecond time region, right? So we have enough time that one molecule upon excitation it can stay for a longer time. What is the fluorescence lifetime? It is the nanosecond time scale. So you can see within the time scale it can stay for a longer period of time. So at certain point of time you do not have anything. I will show you some of the real data. So here is the offstate is being created, right? And that is whatever the beauty it is. Now if you go for a simple spectrophlorometer, whatever you are measuring in the lab, so you can see this is there are several types of spectrophlorometer. So whenever you shine the light from the spectrophlorometer, if I have the sample here, so the light has a certain kind of diameter, let's say 2-3 millimeter. So if it is going to the sample and there you have the detector, so what it happens, because of this Brownian motion of all these molecules in the solution, at the time of measurement, whenever you are exciting, you will have at least 5 into 10 to the power 10 number of molecules if you are using 15 micromolar concentration of the sample. So what happens basically, you are ending up with this kind of broad spectrum and you are losing all the informations whatever in the single molecule level, and that basically not giving you any kind of information. Of course you have some kind of bulk information, but that is not enough for the high-end, high-level applications. I hope you understand what I am telling, that this is the light source basically, this blue light. So you can see that the molecules are randomly moving, so you do not have any kind of control and you have the lot of unwanted signals which is basically possible. So what could be done? On that case, it is better if we can select one of them, right, and then take the spectroscopy. And this is what the microscopy comes into the picture, that you can tune in at the single molecule level. So what you can do, you can modify these microscopes. Right now we have lot of your commercial available microscopes as well, but one can build also. So we have our custom built microscopes as well. So what we do, we can manipulate both of these things. We can manipulate the solution level as well, and we can do in a fixing sample. So what we do basically, so you can see here the same techniques are being used here, that we have the light source here, so which basically we are using the light source, and then we can have one dichroic mirror. Dichroic mirror, the purpose is that it will pass the light for the sample and then it will give you the emission sample by not passing the excitation sample. And in the cover slip, this is a cover slip and there is a stage. So in the cover slip, what you do, by using the spin coating technique, simple spin coating technique, if you are having the slides is rotating in a 3000 or 5000 RPM and then you are putting one drop of nanomolar concentration, you can end up with this kind of individual particles is sitting in this here, and then you can move this stage, and whenever this stage is coming to the central point, whenever the light source is coming, so you can excite a single molecule at this point, and you can record the photons which are coming from the sample, and then that could be captured in the detectors. It could be a single detector, it could be multiple detectors, and then finally you have the controller, and in this controller with the computer you can have all this kind of photon counts from a single molecule, and then you can average them out. So earlier what it was basically here, it is a clubbing of all the molecules together, right? So you have the background signals as well. But here what you are doing in this scenario, you are doing the same thing but at a single particle level. You are capturing each of these individually, and then you are seeing that kind of dynamics of this blinking or whatever, or the triplet state, and then you can have individual molecules or individual molecular materials information.
Do you require low density of scatter for this thing?
Yes, yes, definitely. But it would be good that if you have the quantum field high. Quantum field low also it is possible because it is a single molecule techniques, so it's not a problem, which is difficult in case of spectrophlorometer, and that is why you see that we have varied amount of spectrophlorometer, like you see Horiba, they sells this fluorolog 3, they have the signal to background ratio is 30,000 by 1. Then you have Hamamatsu, all these things, they are having low quality. So that basically the restriction because of the solution. But here what you can do, as you are doing in the single molecule level, so even minimum number of photons are enough to capture, because these detectors are the highly sensitive detectors, which is, we call it as avalanche photodiode, or we have the MCCD camera as well, so which can detect single photon very easily, right? Now, so what it basically does, so you can see here that I have the laser, we have the objective. So here at a certain point of time, one molecule I can capture here, and then we can have this individual blinking, and then if you have a monochromator you can put it here. Even for a single molecule you can also capture the graph, and then all of this graph could be merged together to get your that absorption spectra as well. Not only that one, those kind of blinking events you can see with time. So this is in the mind, the photons or the photon burst you can see here, that basically gives you the real time. If you go to the next slide here, yeah, you can see here that whenever I am now capturing one of these molecules, I am putting in the detector, I purposefully move the stage, this piezo stage, and then put one of these here, and then you can have either this kind of phenomena or we can have this kind of phenomena. What are these two? This is basically the blinking events. So sometimes it is in the off states, and these are basically the individual on states. So these are number of photons. You can see this is kilo counts per millisecond. So 1 millisecond pe how much counts we are detecting. So each and individual photons are coming, and that's what we are capturing here. So there will be multiple things that it could have the blinking phenomena as well as the single step bleaching. So the single step bleaching is basically, which is basically almost all the times is being signing. So this could be done by switching over by using two different type of lasers. So you can create one bright state as well as the dark state purposefully, and you can do also redox reaction here. You can see that we have some kind of electron acceptor or electron transfer reaction, and in this way you can understand at a single molecule level what is the redox reaction going on or what kind of electron transfer is going on. So this is basically in a cover slip experiment where you can fix the sample. The other one is basically, I hope some of you might be knowing, fluorescence correlation spectroscopy, which basically what it does, it basically does in the solution phase. So what it do basically you want to have a confocal microscope. In confocal microscope, again you have this objective, and due to the arrangement, I am not discussing too much, due to the arrangement which basically defines by the pinholes basically take out the stray lights or the other lights, otherwise it passes only the sample, only the light coming to the sample. So what you can do, the same diffusion what is happening because of this confocal rearrangement, the laser light is basically falls like this. So the laser pointer, so the focus is here, you can see here. So at a time what I can do, I can capture only one molecule, right? And this also being done because of this confocal volume. This is, we call it as confocal volume, which is basically in principle 10 power minus 15 femtoliter, 10 power minus 15 liter, which is femtoliter. And if you have nanomolar concentration, so if you have femtoliter minus 15, nanomolar is minus 9, so it is basically minus 24. Now if you divide by the Avogadro number, what it is basically, it gives you 0.6. So basically what you are doing at a certain point of time, you are capturing the events of a single molecule. although it is not exactly single molecule because the molecules are moving around, but whenever you are capturing the signal from the detector in the central point, you are capturing basically one molecule. That's why it is the beauty. So you can do also in the solution phase spectroscopy also. So what happens basically in this case, you will have a series of dynamics. Series of dynamics means in a molecule or in a molecular materials, we have different type of dynamics happen. You can see here that this is basically diffusion. You can see the time scale. This starts from the picosecond to the second. So you can see the diffusion. So the diffusion basically happens from microsecond to second scale. And then here is, sorry, yeah, millisecond to second scale. And then you can see triplet state. As we talk about the triplet state fraction. So triplet state dynamics is basically in the millisecond and then ranging from here also. Then we have the rotational fluctuation. What is rotational fluctuation? If we have the anisotropic molecule, right? An isotropic molecule, what it is happening? Whenever it is rotating, you have nothing. But let's say carbon nanotubes or the nanorods, what it happens basically? It has the two different type of dipole moment. So whenever it is rotating in this way, or if it is rotating in this way, or if it is rotating in this way, this is different. So on that case, what happens basically? You have the rotational diffusion different. And this rotational fluctuation or the rotational correlation also you can capture here, which is basically in the nanosecond time scale. This is we call is a rotational correlation time. So this is diffusion time or the fluorescence correlation time. This is triplet state time. You have the rotational time. You also have the anti-bunching. Anti-bunching means anti-correlation. This is we call it as correlation, and this is we call it as anti-correlation. So all the information. Anti-correlation means whether two molecules are interconnected with each other or they are apart with each other. The time scale is different, but within this setup, you can have all these dynamics starting from picosecond to second. All these informations you can capture. Just you need a detector which can capture these kind of events, because all the detectors are not enough. Like if you measure the fluorescence lifetime. So what you do basically, you measure the fluorescence lifetime, which scale? Starting from nanosecond to some kind of microsecond, right? Because we cannot go beyond. So if we go for the microsecond time scale measurement or millisecond to second, we need to have a different detector, which we call it as phosphorescence detector. That is a different, right? So you have different type of detector. But in principle, what you can do the correlation, and then you can do different type of dynamics. You can do different type of size measurement by the correlation time using the Stokes-Einstein equation. Also, you can manipulate this information and to get your different information, right? So this is all about the basics and fundamentals, understanding from the fluorescence to its fluorescence blinking, and then the single molecule spectroscopy, then confocal microscopy. Whenever we are doing about the single molecule spectroscopy, we have either fixed sample or we have the solution based sample and their fundamentals. I hope it is clear to all of you. If you have any questions, you can ask me right now or we can discuss later on, because now what I want to do, I want to show now that two different type of directional research where tuning of blinking is extremely important to highlight their beautiful applications. So the blinking has both advantages and disadvantages. So first of all, I will show what is the advantage of this one and how it is being manipulated for capturing high resolution image or the super resolution image in case of biological samples inside the cellular environment. So that's what my first application. So that blinking basically generates super resolution microscopy. And the super resolution microscopy, what it does basically, it basically manipulates the images, whatever is being captured either in a single normal wide field microscopy or compound microscopy you can say, or even confocal microscopy you can say. You can see here the image are very blurred, but this is not enough. So can we manipulate that one to get this kind of beautiful resolved structure? And that is what the play comes of the blinking. So because of this blinking, there are two super resolution microscopic imaging generated. One is called stochastic optical reconstruction microscopy. The other one is called photoactivable localization microscopy. Both the principle is same, where blinking is being used. So what it basically does, I'll explain in the coming slides, but what it basically does, it basically manipulates this confocal volume. Let me discuss in the coming slides. But before that, why this is so important? As I told you that whenever you are using a confocal arrangement, so you have this all this setup what I have shown, that you have the light source, dichroic mirror, here is the objective, here is my sample, and the sample we can think about that this is the objective, and here is a biological sample, let's say cell with a nucleus with all of its organelles. So what happens basically here, whenever this light is shined to the sample, because of the diffraction limit, the fundamental laws of the light, what you could end up with? You could end up with a volume of either 220 to 250 nanometer in the axial direction, sorry, lateral direction, which is xy direction, and in the axial direction in the light passes through, then you have the 500 nanometer light, sorry, 500 nanometer spot. What do you mean by this? This basically tells that even if you have a 1 nanometer object, let's say molecule, if you think about any kind of dye molecule, cyanine dye or auto dye, or even this molecular clusters, 25 nanocluster, which is 1.2 nanometer to 1.3 nanometer in size, what will you be ending up whenever you are shining the light? If you do the imaging, you will be ending up with the resolution is 0.61 lambda by Na. So if you think about the numerical aperture as let's say 1, so if you are using a 500 nanometer light or 600 nanometer light, one single nanometer you will be observing as a 300 nanometer if you are using 600 nanometer, and in the axial direction it will sorry, it will have a 2 lambda by Na square, which is basically double of that one. So even for a 1 nanometer object, you will be ending up with 700 or 800 nanometer. Now if you go to the organelles, you will have lysosome, mitochondria, which are very, very small in size. So on that case, you cannot see the interaction in between them. That's what the super resolution microscopy come into the picture. And as you see here, the time scale, sorry, the size scale. So whenever we are going smaller to smaller to smaller, and then as in the morning also was being talked by Professor Pradeep regarding the virus capturing the TM image. So here also the same thing, you can see the virus falling within this region, and if you go to the smaller size proteins or DNAs or the small molecules, here even if you have the 1 nanometer, you will have the 250 nanometer resolution. So 250 nanometer is the limiting power, and you have this kind of blurred image. So one should have this kind of beautiful images, and that is the beauty of the super resolution microscopy. So up to this point is fine, but whenever you go beyond this one, which is within the diffraction limit, then the problem appears. And that is what the super resolution does basically. So what basically it does? It basically manipulates that point spread function. What is this? Point spread function, whatever I talked about, this is basically we talk about the point spread function. Point spread function is basically a Gaussian type of function, which basically in xy direction it gives you the full width hub maxima as 250 nanometer. In the axial direction it is around 500 or 600 nanometer. So what basically it looks like in a 3D curvature, in the 3D curvature it looks like this one. So I have this one as 250 nanometer in the full width hub maxima, right? So in case of this blinking, we can manipulate this one to sharpen as minimum as possible. So you can see this is basically the manipulation of the blinking. So on that case, if a image is having two such kind of particle where it is unresolved, you can see only one. If you can do this one, so you have two different type of population, and that basically resolve the images, and that basically beauty of the blinking. If you go to the more little bit classical way to understand how it is blinking, so let's say we have this kind of, let's say 16 fluorescent either molecules or molecular materials are clubbed together. So what you see, you are seeing a completely clubbed image. You have seen in the stadium, right? Whenever you see this cricket stadium, we have this floodlight. So in floodlight, what it have? You have multiple number of halogens, right? So if you see from the far long, what you will see? You will see a single light. You don't know that they are separated basically. So how we can separate them? We can separate them by blinking. How we can do that one? Let's say I have 20 such halogen light in a single frame. I have on only one light, the others are basically off. So off means within that blinking time scale, these are off, this is on. So what we can do? We can capture that position by by capturing the point spread function maximum intensity, and that's what here is being done basically. So you can see that in a next frame, completely dark, if we see, now I have this 4 particle basically glows. Out of those 16, at a certain point of time these 4 are glows. So if this 4 is glowing, so what we can do, we can capture the point spread function and then we can take the maximum position in the middle, because point spread function intensity where it is in the middle position. So what I can do, I can mark them, right? So I have marked them. So it means that I have this kind of glowing object, I have now minimized this one to this point. So I have modified this point spread function, which was 300 nanometer, now it is reduced to this one. So at a certain point of time, these 4 are glowing, the others are not glowing. In other point, what will happen? So we have marked this one, and the other point, this 4 will be again certain point of time it will be glowing, and the others will be dark. On that case, again we can mark them, and then we can tune this, manipulate that. So in a way that I have marked now each of this point, so I can reduce all this intensity, whatever is the outside for each of these, and then I can get this one only. So you can see that we have reduced the unwanted signal, right? And that's what basically happens. So finally, if you see here that now let's say this is a ring object, and now I have stained or I have marked with some kind of fluorophore here. So if I have one fluorophore, two fluorophore, and then multiple fluorophore, the object is not visible. The ring is completely covered, right? So you don't know whether there is a ring or it is a cubical structure or it is a square or it is trigonal, whatever, we don't know within the size frame because of this lambda by 2na diffraction limit. Now, if the blinking come into the picture, so what will happen? So this is my one object and I have marked this one, right? In a certain next frame, what we can do, we can have blinking. Now you see each of these are blinking and then I am marking. So this is the beautiful thing what you can do here. Finally, you can see that whatever the inside you have it, now it is completely vanished. So you will have a very nice ring structure as well, right? So that is the thing the blinking basically does. And you can see the blinking here. So this is basically the off state we can think about, and in certain point of time it is on. So this is the number of photon, and then after a certain point of time it is completely off. So in this off time frame someone was on, so I can capture, and then other time frame someone was on, I can capture, and in this way we can reconstruct this one. So the beauty is that whenever I have excited, some of them are in the off state, and because of these off states I can capture the on that time which one is on, and that basically marked, and then you have the super resolution imaging. Now if you see a real dynamics video here which was again captured, you can see here that this is stochastically happening and we are reconstructing. So what is basically happening here? So they are blinking stochastically, and that's why it is called stochastic optical reconstruction microscopy. So they are blinking happening stochastically in a time frame, and we have captured each of these images. As you can see here that these are all basically starting point. So at a certain point of time they are blinking, so we are marking and then reconstructing. So stochastic optical reconstruction. So we are reconstructing the images, and this was your confocal microscope which was being reconstructed with a beautiful background free, more resolved structure. That is the thing is being done in case of super resolution microscopy. And we work different type of materials starting from molecules as well. So I will show 2-3 examples here. Like we worked on carbon nanodots, I think some of you might be knowing, which is very, very interesting as well as the complex material to understand first of all. So we worked for last 10 years in this carbon dot. We are working on quantum dots, we are working on nanoclusters. So I will show you the first example, I will show you the nanoclusters, and then we have several other materials as well, spions, super paramagnetic iron oxide nanoparticles. So as you know that what are the importance, because whenever we are working on the organic molecules, they are suffer from certain kind of limitations. What are the limitations? Whenever you go to the biological samples, they are either not biocompatible or non-toxic, because whenever you are working on a sample, it has to be non-toxic, otherwise it can give you some kind of problem, right? At the same time, it could be photo bleach, as the environment is there, so that can help in photo bleaching. So it can do faster photo bleaching, and you cannot capture images for the longer period of time. So in that case, you can have some kind of materials which has the high quantum build as well as the non-toxic and are biocompatible in nature. And that's what the molecular materials or these quantum dots or the other materials come into the picture, which are basically giving you a lot of advantages with that disadvantage of this blinking. Although I can say but we have this kind of materials have highly photostable and bright, high quantum yield, non-toxic and biocompatible, and long-term photostable within cell. You can capture even 12, 13, 14 days. I will show you some of the images as well. And obviously, as I told you, this on-off blinking, we can do the manipulation in these kind of materials. And as the quantum yield has to be high, so we will also have the photon counts, because in single molecule, we basically measure the photon counts. So what we do basically in this case, in the biological part, so in the biological part, we have this kind of different type of materials starting from, let's say, blue to red or even far red. So we conjugate some kind of simple chemistry and then conjugate with some kind of some kind of targeted molecules, and then we stain them and we can image them, several of these like actins, microtubules, mitochondrial lysosomes, as per your choice, right? So, this is my single molecule setup, which is custom built. So we have different type of laser systems starting from blue to red. You can see they are very, very simple and cheap. These are all continuous wave laser. It is cost is very less. So here you can see all these 4 different lasers, and all this together we can put here in the microscope, and then we have the camera here, and we can detect the signal with these optical properties. So that's the thing what we have in our case, and the same setup could be used for the super resolution microscopy as well. So the first example I will show you the imaging of lysosomes. Lysosomes are very, very small in size, which are basically 50 to 500 nanometer in size, and lysosome everybody might be knowing how important it is. If lysosome could not have been there, we could have died immediately, because lysosomes are the suicide bag, right? Whatever the unwanted, unwasted materials in your body you have, lysosome, because of these hundreds of enzymes, that basically clipped and clean our body. That's why you call it as lysosome. So lysosome has a lot of role to play. I'm not going to that biology, but just want to show the images how we capture. So lysosome, one of the purpose is to do the autophagy. Autophagy is basically killing the unwanted cells. You can see here that they can come. So on that case, it is very informative that if we can see how lysosome moves from one place to another place, if we can track them in a real time, whether they are coming contact to the other molecules, how they are behaving with each other, that's we can do in terms of the imaging, right? Okay, so I'm not going to this one. Professor Pradeep already talked about the molecular materials and all these things. So here what we do, basically we are using a protein conjugated nanoclusters. The purpose was simple, because this protein, which is called as a bovine serum albumin, it has the very prone to go to the lysosomes. So by inherently we have designed this one so that it can go to the lysosome for the imaging. So this I'm not going to this synthesis process, because this is not my job as well. So but believe me, we have all these characteristics techniques, whatever I have done, and you can see they are basically red emission here. They are very, very nicely red emission, and their particle structure as well, which are little bit not so homogeneous, but it's okay. Whatever we can see here, that we have BSA conjugated gold nanoclusters, which was 25 atoms, whatever morning was being told, and the silver is 30 number of atoms. So we used both of them, and then initially what we did, we checked the several type of biological understanding, because as I told you that the biocompatibility, the non-toxicity has to be checked first. So we check the viability or the non-toxicity, and you can see that we, even with the high concentration, they are highly non-toxic. So these are very, very important materials to capture, and also they are quite stable within the physiological range of the pH, starting from 4 to 8 pH. So their intensity is quite stable, right? So within this one, so we captured, first we stain them with the lysosomes, and then we capture the images. So you can see here, this is a simple confocal image. I will come to the super resolution image as well. So this is the simple confocal image. So what we have checked first, that whether these nanoclusters, whether they are really staining to the lysosomes or not. So what we do, we did the co-localization with some kind of commercially available, which is called as a lyso tracker. This is in the red region, this is in also some of them in the fur region. So you can see there is a very nice co-localize with them with a Pearson correlation coefficient, which measures basically how much they are close with each other. So that basically 89%, which is quite extensively high. Normally, if you have 70% or 0.7, we can tell that they are co-localized. But here you can see it is highly co-localized in both the cases, AU and AG, right? And then we also check the long term tracking as well. So you can see both of these clusters, 1 day, 5th day, 9 day, 13 day, up to 13 day they are quite stable. Although we are not shining the light throughout 13 days, there is a sequential gap, but still you can capture till 13 days without any disturbance with the image. While if you use this lyso tracker red, even it is within 3 days it is just vanished. So you can imagine these molecular clusters, whatever we are talking about in the morning, how beautiful it is in a different direction, where you can apply these things for biological applications, and that too in a super resolution application as well. Right? And then next we observe the mitophagy, which is basically the lysosome when comes contact to the mitochondria, and this mitochondria was labeled with some other probe, and this lysosome was tagged with our nanoclusters, and you can see that in this case we can have the video as well. Yes, you can see here that lysosome and mitochondria are close together. In some of the cases there are some yellow spots. Yellow spots basically green or red basically merging together. It means the lysosome come into contact with the mitochondria and they are clinging to the mitochondria when they are basically not working. Here also with a time dependent manner, you can see that in case of these two different materials, whenever they are far apart, there is no co-localization, but with time gradually that red and green they are merging together and we can have the yellow spots, which basically telling that mitochondria and lysosomes coming in contact with each other. It means the lysosome is taking the mitochondria and then killing themselves. Right? So I think I'm running out of time. So this is basically the lysosomal dynamics. You can see one can track each and individual lysosomes here and then calculate the velocity within the periphery of the nucleus and also outside of the cellular environment. And then we did a lot of analytical understanding about the velocities by tracking each and individual lysosomes together. Let me move a little bit faster. So this is again, now it is the super resolution microscopic image using the gold nanoclusters. You can see that it was confocal image. Now if you go to the super resolution, you can have very nice beautiful images one can see. And here we can able to capture the each and individual lysosomes here inside the cellular environment, and you can see the each and individual. So if it is the confocal microscope, we have this kind of broad spectrum, but in case of super resolution, we can capture each and individual lysosomal position here. You can see the distance in the micrometer, and we can have up to 59 nanometer resolution we can achieve, which was not possible in the confocal microscopy. So that is the beauty of the blinking here. Even we have performed this one with the help of our collaborator in USA, Professor Giorgio Dio in University of Cincinnati. So they basically works on the brain organoids. So we send their our samples to them, and they capture these images using the super resolution microscopic technique, and one can see that it can go up to 114 nanometer depth, sorry, micrometer in depth in a tissue, while in case of the normal probes it can go up to 80 nanometers. So it has the one another property that it can go or penetrate without losing its intensity. Then some kind of other works also we have done in case of the C. elegans. C. elegans is one of the worm which is basically used as a model system. I hope you can read about the C. elegans. It has the similarity in the neuronal functionality close to our human neuronal close to 70%. So that's why it has been taken as a model system, and we can see that these kind of materials could be used, the dynamics of the evolution of the C. elegans starting from a single cell or two cells to a fully matured C. elegans. So it can show you 16 hours of the capturing of the images inside the lysosome, and this is all basically in the molecular materials. And the second one is the carbon dot. So I'm not going to the details of the carbon dots here, but one important thing, whatever people are working, so I worked for last 10-11 years, be careful while you are working on the carbon dots, because it has a lot of complexity because of the synthesis process. We do not know until and unless you are sure about what it is. Please be careful while you are working on the carbon dots, because it can create a lot of mess, because the synthesis process itself give you lot of unwanted products, and one has to be careful. So initial thought was that carbon nanodots is that as a core structure, and then you have the molecular or surface states, and it has an excitation dependent emission. But later on people found out that it has also an excitation independent emission. So if you have an excitation independent emission, so it is a molecular fluorophore like behavior. If you have excitation dependent emission, it is a molecular material like behavior. You remember this one, this is the absorption spectrum we have shown in case of molecular material. Here it is having. In this case, this is also similar to a molecular absorption spectrum, molecules. but people have reported as a carbon dots. So there are a lot of things one has to understand. So going to the further, without going to the further details, just wanted to summarize here that this is a molecules which is having a absorption, emission, excitation defined. In case of the carbon nanodots, it is not defined, because whenever you have the emission, you have a broad absorption. Whenever you are exciting, you will not end up with the maximum emission position. Somewhere else you will end up with the maximum emission position. So that's the thing one need to careful, and that's why carbon dot is a field. It can have, whenever you are going for the top down approach, you can have different type of inhomogeneous samples. So one has to be careful. I'm not going to the details of all these things, because I want to show some other things as well instead of. So depending on the different synthesis method, as I told you, if you go with time, you can have molecular flow for light structure, and then finally end up with the carbon dot. Here also you can see, this is a very nice JAX paper where they have changed the temperature 180 to 400 degrees centigrade. These are the molecular flow for, and with increasing the temperature, this creates a carbon dots. So if you don't know which condition you are using, you have different variation of the structure, and you can have end up with different type of structure of these kind of things. So actual carbon dot might not be present all the times. It might be present only 5 or 10%. So one has to do a very nice thorough investigation, and that's what we propose in 2019 in Nature Communication, that one has to be careful and do a very thorough study by purifying and then understanding what are the structure. So that's the important in carbon dots. So anyway, without having these things, then what we did here, we did all those procedures, and then finally we got very nice carbon nanodots with emission of 612 nanometer, and then we did the single particle study as well to understand the photon behaviors, and then finally we did simple chemistry, click chemistry, where we end up with this carbon dot with the actin filament. So this is, you can see the images of the actins in a cellular environment, and this is basically Duffy staining, which basically they stain the nucleus. And then we did also the imaging of the fluorescence with a known GFP proteins. This is the carbon dot, this is the GFP protein in the same C. elegans model, and you can say they are very highly colocalized with each other. It means that they are very highly selective to the actin filament. So you can do a lot of chemistry. And then finally we did the super resolution imaging of the actin filament. So this is the confocal and wide field image. This is the super resolution image. So you can see the structure is clearly visible up to 76 nanometer in the width of the C. elegans. Okay, then we did another experiments where we try to understand the dynamics of the nuclear DNA, which is basically made up of simple nucleus units, DNA units. Then they wrap together, gives you the nucleosomes, which is basically 3 to 10 nanometer size, and then you are ending up with some kind of chromatin structure. They are basically, we call it as heterochromatin or euchromatin, that has a size of around 30 to 100 nanometer, and then finally you are ending up with a chromosome. So this kind of understanding we try to understand. On that case, carbon dot again was manipulated by simple click chemistry so that it can stain the DNA or the nucleus inside the, DNA or the chromatin inside the nucleus. And then we did the understanding the cell divisions, which is mitotic cell division. Schematically it is here, that starting from this phase to finally this phase, and you can see here we have done all these images very nicely in a cellular environment. You can see the images also. This is cell division starts from prophase to metaphase to anaphase to telophase, and you can see that the DNA was stained by the carbon dot. This was not divide, this is organized, the chromosome in between, then cell division starts, 2 nucleus, and then we have these 2 different, and there are the super resolution structure here. Okay, let's keep this one. And then we also did the DNA dynamics, DNA fragmentation, starting from the normal 0 hours to, by using a paclitaxel. Paclitaxel is a very effective drug for the cancer treatment. So we try to understand that whether paclitaxel really damaging the DNA. And you can see we have done a systematic study up to 24 hours, and one can see that it has basically killing the nucleus by damaging it. So it was a very nice nucleus structure. Then they are having deformed, and then they are forming multimicronucleus, and then they are fragmented. So we can capture the images by this super resolution technique. Okay, so this was the disadvantages. Now I'll take another 5 or 7 minutes to another way of understanding, and one of the other important research field, which is basically the single photon emission. room temperature single photon emission is rather important because it has a lot of applications in quantum technology, and I hope now everybody is knowing what is quantum technology is. So, quantum technology is basically we are using the quantum theory. Earlier or so far, whatever we were using in a computer, that is basically classical concept of 0 and 1, right? Of the codes, whatever we use in a computer, it is basically 0 and 1. So, I have two simple states, right? Now, this quantum technology comes into the picture. I will take 1-2 minutes to explain, but it has a lot of applications. It can do solving complex problem. It can do further communication, safer communication, faster communication. It can do the navigation. It can do much more accurate measurement and all these things. So, what it basically does, that whatever we do these days, the measurement or the computational facilities, that could be exponentially faster if we go for the quantum technology. You can see here that whatever the if you are increasing the complex size, and if this is the time of solution, so in a classical way, it will take, for the same complex problem, it will take years to solve, but if we go for the quantum technology, it can take only few weeks as the complexity increases. So, that is the beauty of this quantum computer. So, how it works? It works basically the form of the Schrodinger cat. I hope some of you might be knowing what is Schrodinger cat it is. So, it basically what it tells, that if you have a closed box, and in a closed box, if you put a cat or any kind of animal, and if you put some kind of poison, and then you completely cover it, black it, right? So, what could be the probability? If you have the poison, you don't know what is the amount of the poison. So, what could happen? Either it could be dead, or it could be alive, or it could be in between them. You don't know because it is inside, right? So, that is the thing actually, and that is the thing being used in the quantum technology. So, it being used basically, as you can see here, that classically we had 0 or 1 state. In case of spin, I could have either upward spin or down spin. But if we do the superposition means either it could alive or it could dead. So, we can take the linear combination of those things. So, these two states could be as a 4 states, as it could be also in the spin also. So, I could have both upward spin or upward downward spin, upward downward plus minus. So, I have 2 states, I am creating 4 states. So, it means that classically whenever I have used 2 things to compute, here I am using already 4 states. So, you can see here that even if I am using, if we call these are the bits, so 2 bits basically 1 qubit, 4 bits 2 qubit. So, if we end up with a 1024 bits, means for a same problem, if you are using 1024 bits, I can have only 10 bits to compute, right? So, it means it gives you the faster communication or faster problem solving. So, that is the beauty of the quantum computer. So, we are using 50-50% superposition of either the electron spin or the photons. So, there are several ways we can do it, and there are several materials as well. So, we can see here that how it is increasing. So, that is what the purpose, but whenever we talk about the single photon emission, quantum technology, one of the important criteria is that one has to have the single photon emission. And single photon emission has certain kind of properties. I am not going to the details at the moment, but it has to have a anti-correlation. Single photon emission means at a time we are capturing only one photon. You remember I gave a graph of this solution phase measurement. Here we had in the right hand side I had the diffusion, then we have the triplet state, then rotational, then anti-bunching. So, this is the anti-bunching, basically we are measuring the anti-correlation. So, if we can measure the anti-correlation, then we can think about the single photon emission. And in this case, of course, there are several materials. From the morning we are listening also, we have all these materials are being used for the single photon emission, but all these things are not good enough in a room temperature single photon emission, because all this works under the millikelvin temperature. Why? Because these materials, that spin state created or this qubit formation are not stable, they are very temperature sensitive. So, on that case, if you have, let's say this is the chip of the quantum computer, all these big setups are required to cool down, because it has to work in the millikelvin. You can imagine millikelvin means it's almost 0 Kelvin, 0 temperature. So, that's very a challenging task, although people are working, and we have just yesterday I got the message that Stanford, they have got this 50 qubit for the first time in even in the millikelvin temperature. But anyway, so that has this kind of thing. So all this basically works in the millikelvin temperature. So it would be good that if we can have room temperature single photon source. And these days, if you can see, there are very nice articles are coming in Science Advances. There are several papers also. They are talking about, here it is carbon doped boron nitride. Here perovskite is quantum dots. We are listening all these things. So they are basically applied cadmium selenide, zinc sulfides. So they are also working on the room temperature single photon emission. So the fields are emerging. So inspiring by that one, we were interested that if we can design some of these kind of materials. So we are working on some of the quantum dots. Then what we found out, again the same problem, that here is the blinking. So blinking here plays the role, which basically deteriorates its brightness as well as the single photon emission. So what we have done in this case, we have tuned the materials by incorporating selenium. I am not going to the details, but we have different 4 type of materials. And then what we have observed by using the single photon techniques, we have measured the photon counts. Whenever we are increasing the selenium incorporations, the single photon emission photon counts increases. It means brightness is increasing, which is one of the important criteria for the single photon emission. It is very beautiful that it has doubled 13,000 to 26,000 by incorporating the selenium, right? And then if you want to measure the single photon nature, as I showed you in the solution phase, here is basically a technique which is called it as Hanbury-Brown twist. We basically first give the concept of how to capture the single photon. So how it is basically, so you have the light source here, and then you have a beam splitter, 50-50 beam splitter. So the light goes, photon goes like this. We have the 2 detector here, and then is the correlator. Now if you have a large number of photons coming here at the certain point of time, so if let's say 10 photons, so if you merge them, so you have the 50-50 chance. So you, on that case, you have the 50, in this case you have the 50. So this is not anti-correlated, they are correlated. So these are not single photon, right? So on that case, what you could do, if we have a single photon, so now if a single photon is coming, so either it will go this or this. So it's basically, if you are having this correlator, so correlator, what you will see, either it is coming either this direction or this direction. This is basically anti-correlation, and this is anti-bunching, and that basically gives you the anti-bunching value. So low correlation, and that basically defined by this factor. So minimum is the correlation, more is the single photon emission, and that's what we did. And very nicely, for the selenium incorporation, the value of the G2 factor goes to 0.02. I think I forgot to keep here, but it is 0.02. 0.02 means close to 0. So it means highly anti-correlated. So it gives the anti-correlation parameter. And here blinking plays a role. So whenever we have the, we do not have the selenium, so we had large amount of blinking. And this blinking basically played the role of reducing the photons. But whenever we incorporate the selenium, you can see this on state is basically increases, and you had this blinking parameter from here to here, it is increases, and number of photon increases. So here we have tuned the blinking, here we have reduced the blinking. So earlier, whenever we talk about the super resolution, we increase the blinking because blinking helps to position each and individual probes. Here what we are doing, we are reducing the blinking because blinking is not good for the single photon emission, as it reduces the brightness by creating the offstate. So beautifully, by incorporating selenium, we had these on time increases from 4 to 24, 1 orders of magnitude on time increases. So basically brightness increases. So that's what basically in terms of the single photon emission. So in conclusion, I can say that whatever we are doing or whatever I have discussed, it is basically single molecule techniques or single particle techniques, which basically tune the single photon, which basically tunes the blinking events. And these blinking events are very important. Stochastically, we can modify them, and using these blinking properties, we can end up with 2 different extremely important application. One is super resolution microscopy, and other is quantum technology. So with this, I hope that the single molecule techniques or the single molecule materials, and these molecular materials, as Professor Pradeep was telling in the morning, that what are the other directions of the molecular materials. So I have shown one of the examples, and it could be multifolds if we understand their optical properties in a single molecule level, and hopefully we will be contributing in the future in that direction sometimes. Thank you all. And obviously this is my group, without whom this is nothing basically.
Thank you, Professor.
I have a very general question. Actually.
Yes.
That is, from a materials perspective, how are we introducing this off state in certain kinds of materials? Like you showed that cadmium telluride, you were doping with doping. Am I right? You are doping with selenium.
Yes.
So, what is in general the property which we are trying to see?
See, yeah, I understand. Any further question or this one only? So from the morning, this is the discussion going on that it depends on the materials itself. You have to understand. Please sit down. You have to understand that what kind of application. My goodness, what kind of applications and what is your requirement. Depending on that one, we have to purposefully select the materials. We need to first understand their individual optical properties, and then only we can think about that how that could be manipulated. So here the purpose of using selenium in case of single photon source, because whatever we have observed, the selenium itself has a low quantum yield, right? So on that case we have seen the quantum yield decreases in solution, but whenever we incorporated inside the cadmium telluride, what happens basically, it basically at a molecular level tune the band gap of the cadmium, and that increases the single photonicity as well as the brightness which is coming from a single cadmium thing. So it is again depending on, it is not that it is universal. This is, I have shown that it is working as a single photon emission, but it is still not ready for the device fabrication, because there are other parameters. There are at least 5 parameters one has to work for the single photon emission. One is obviously brightness. The first and foremost important, obviously the photon counts, but at the same time we have to have the very low lifetime, small lifetime, as well as it has to have the very small bandwidth. If you have the large bandwidth, so it has a homogeneous broadening, so that will contribute in your impurity of the single photon emission. So there are several parameters and aspects we need to work on. So this is the first example we are showing. Now we are planning to work on the perovskites material, because as we see that perovskites has a highly efficient materials in terms of the several aspects. Only important problem is the perovskite is the stability. So if we can do these things, then I think this quantum technology will take a leap with the perovskites material.
It's a very nice talk.
Thank you.
Sir, Doc, can solvent play a role in the fluorescence blinking?
Yes, that's what the very first example was given. The fluorescence blinking one observed in a molecule first, not in a materials. So because you see, initially whatever the biological sample imaging what has been done, that was done within using the dye molecule only, right? So in this dye molecule, we have the triplet state, but we do not have that kind of off states. So the solvent or the buffer plays an intrinsic role creating those off states. Even the redox molecule, there is very beautiful paper by in Germany, Philip Tinefeld. So you can follow their paper in 2008 and 9. There are 2 angiochemy paper. They have just simply incorporated the radical cation, radical anion by using the solvent or some kind of media. They beautifully created this on state, either positive charge or negative charge. In case of carbon dot, we also used and created positive radical cation. So you can do it. That was the first. But in the material we have already intrinsic. You don't need to do anything. Now you need to understand which material is good for me, and then you can work. Because if you have a hundreds number of trap states, then it is difficult to control. If you have a biexciton as well as a positive trion, negative trion, it's hell lot of things to control. Their time scale is completely different, right?
Because biology is so complicated.
Yeah.
For your super resolution imaging, your materials you will have to stain or you'll have to chemically different kinds of molecules have to be put so that they anchor onto all the biological objects.
Exactly.
How do you control that?
The control is that again the selection of the molecules or the molecular materials. We first see that how fluorescence intensity it is having, and then we can do little bit surface chemistry. As I told you, that simple click chemistry will be helpful. So let's say I can design myself, like in case of the protein molecule, as I showed you, the gold nanoclusters. We purposefully use the protein BSA because it has directly prone to the lysosome. Then in case of actin filament, there is a molecule called phalloidin. So what we can do, we can manipulate the surface of these molecular materials with a functional groups with this phalloidin. So in phalloidin we have the amine group NH2. So if you have a carboxylic group here, so you can do a simple carbonyl chemistry and then conjugate with each other. That's what is being done in case of this material wherever I show the actin filament. But before that, we need to understand the chemistry obviously of these molecular materials. And it is not that everything will be working for everybody. So we have to understand once again, and optical properties of course is the important. As you see that 25 nanoclusters, either gold or silver, that has the emission at around 700 nanometer, which is absolutely amazing in the red region, because everybody wants in the red region. If you go to the molecules, your photostability as well as the quantum yield is drastically reduced. But in case of these 25 nanoclusters, we have more than 20% quantum yield, which is absolutely amazing for any kind of imaging purpose. And you have seen the photon counts as well. It is coming around 70,000, which is extremely high for any kind of single molecule or the imaging technique.
Your setup also has temperature control?
This one, no, we are working on the room temperature at the moment. But we have another technique which is called SRRF, super resolution radial fluctuation, where we don't need this kind of blinking, but we can do manipulation by the algorithm. This is image software we are using, commercial image software. There you can simply take the videos, confocal videos, and then you can do the manipulation. There I have the temperature controller and I can do the temperature experiment. In fact, some of the experiments I have not shown. My collaborator is in Germany, Professor Jörg Enderlin. So they have this cryo setup. So we have very beautiful optical properties of carbon dots as well as these gold nanoclusters in the low temperature. And we have seen that the photon counts increases orders of magnitude and the on time increases drastically. But in my lab, for the single molecule, you do not have the temperature controller.
The cluster aggregates I showed, the balls, they're all beautifully luminescent.
Yeah. Yeah, that's what I'm telling, that we can, at least we can, now I am, for the last 2 years, I am dedicatedly working on the single photon source. So at least I can try for those, not for the super resolution I have done enough. Now I need to summarize and pack up those things, but single photon emission, I will be happy to test the anti-bunching parameter of some of these, your clusters. If it is working fine, we can see. Yeah. Yes.
What exactly is the influence of temperature on these systems?
Temperature is multiple. Is the simple influence is that temperature basically gives you the collisional increment, and if you have the collision, then simply your non-radiative transition increases and your quantum yield decreases, and that's why if you increase the temperature, your fluorescence intensity decreases. Even if you do a solution measurement, if you remember, see, there you also need to control the temperature as well as cover the cuvette. There are two things. One is temperature, the other one is reactive oxygen, which can gives you the triplet state. So in a simple cuvette, if you are measuring, you just same sample, you measure, even if you are covering this one, same sample, measure for 2 hours with a gap, you will be seeing the fluorescence intensity decreases. So this is because of the triplet state formation as well as the temperature variation. So in a low temperature, cryo temperature, basically you are obsoleting the non-radiative decays, increasing the radiative decays, and you are increasing the number of photons, bright photons, that gives you the quantum yield more. That is the simple thing.